All right, now we're finally done. We spent the last bit of class looking at how do you set up a specific pin on a specific GPIO port. And what you're going to have to do for all of the peripherals is you're going to have to read about the peripheral, look up what its registers are, and then figure out the configuration bits for those specific registers. So the task that I had for you was, how do you make pin PE2 an output, and how do you set that output high? So there's a couple things that you have to do to set up the GPIO. The first things that you have to do is you have to turn on the clock to the GPIO. So every peripheral is driven by its own clock. If you turn off that clock, the peripheral will not run. So I will give you in the lab that you're going to get today a function call that will turn on the clocks. We're really not going to mess with clocks in the class because they have prescalers and configurations, and there's just we don't need to really be messing with how to turn clocks on and off or change the frequency. The main things that you need to do to set up the pin are to set up the mode of the GPIO. So remember, there were 16 different modes that you can put it in. One of it was as a push-pull, which is an output. And remember that there is a mode high and a mode low register. The mode low register does pins 0 through 7, and the mode high register does pins 8 through 15. Once you've set the mode, now you have access to the data in register if it happens to be an input, and you have access to the data out register if it happens to be an output. You write a bit into the correct position in data out, whether you want it to be a 1 or a 0, and if you're going to read in a bit, you read in from the data in register. So what you have to do, as you recall, is you look on these giant tables and you figure out for a push-pull, I need to set the mode bits to be 1, 0, 0. It's a certain field inside of a certain register that you have to set. So you would set it to hex 4. The push-pull configuration means that it can actually sync or source current, but it's how we make it operate as an output. So remember, if we're doing pin 2, that means it is the mode 2 bits. That means that we're going to write 4 to right here. If you took this register and you said PE mode L equals 4, you're going to write 4 to right here. You're going to configure the wrong pin. So what we're going to end up doing today is talking about how we shift and how we mask bits to actually write the data into here and not modify all these other bits. We're mainly going to work with the data in and the data out register. There are other registers that are called set and clear and toggle. So if you want to be unambiguous about what happens to the pin, or if you don't want to go through this read, write, modify cycle that we're going to talk about, you can just write a bit to the toggle pin or the toggle bit. It'll toggle the pin. You can write a bit to the set register. It'll set it. So for your lab, the main things you're going to have to do to turn on a GPIO, it's really only 3 steps. 1, enable the peripheral clock, which I will give you. Set the mode, and then set it as an output. That's about it. For the lab, you're going to do it in 3 different ways. You're going to do it with function calls from the onboard library. You're going to do it with the native data structure, and then you're going to do it with pure pointer math at the end. Now, to access memory mapped I/O, you want to follow a cycle that's called read, write, modify, or read, modify, write. So you want to, because these registers are memory mapped objects, they're always changing. So you never want to use a cached value of the register. You always want to get a clean read. That's why we make the pointers to those registers volatile. So remember, volatile is a keyword that says, hey, I need you to keep this fresh. I need you to look up this value every time and not cache it. So what the practice is going to be is you're going to take a pointer to the register and you're going to read it into some variable, some integer, just making an unsigned 32T. You are then going to do Boolean operations on it to modify that register to have the correct values. So you're going to do shifts, you're going to do bitwise ands, you're going to do bitwise ors to modify the exact bits that you need. You don't want to modify other bits in the register because those could be configuration for other devices. You don't want to step on anyone else's toes. Once you have locally modified the value, you then need to write it back into the pointer. You then take the value that you have locally and you write it back to the memory mapped location. It's important that you do this effectively because it's really easy if you shift by 4 instead of shift by 3. Now you're overwriting someone else's bits, or you're not getting the exact configuration inside the register that you want. So when you're in the lab over the next week, if your stuff's not working, you really should check to make sure that you're modifying the register that you think you are. You can do that in a couple ways. You can just read the register again from the pointer. Another thing you can do is that inside the debug menu in Simplicity Studio, you can manually look up each configuration register. So you can go to the GPIO, you can see what the mode L register looks like. It will manually show you those things, and you can figure out what the heck is actually going on. Now, this is the general method that I want you to follow to modify a register. So you're gonna read the old value, and then you're gonna mask off all the bits that you don't want to modify. Think of it as applying painter's tape to all the bits that you want to keep safe and leaving open only the bits you do want to modify. So this is a binary and you're going to take the value and you're going to AND it with the mask. Then you are going to OR in the new bits, and you're going to modify the value. So let's say, for example, I had a register that the value was just FA. All right, that's just what it happened to be at this time. I want to change this A to be, 3. Whatever, I'm changing the configuration bits, it doesn't really matter. I want this to be 3. If I take my pointer and I say, make it 3, then it wipes this whole register, and the entire register simply becomes the value 3. So now I've nuked whatever bits I have up here. At the same time, maybe you only listened to half of what I said. You said, well, Dr. Forsythe said, I want to OR in the bits that I want. Remember, we're trying to get 0F3. If I take my value, which is 1111, it's not hex anymore, 1010, and I OR in 3, what do I get? Bill, what do I get? I get all ones. So you can't just say equals 3, and you can't just OR in 3, because you're going to get the wrong value in here, or you're going to blow up the entire register. So what you're going to do is you're going to create a mask for the bits that you want to modify. And what you're going to do is you're going to put a 1 in the bit position of all the bits you want to keep. So think of it as like blue painter's tape, like masking tape. I want to keep all of these ones, and I want to discard all of these ones. So if I take F and I AND with F0, my result is then F0, and I've cleared out these lower 4 bits. So let me do this binary-wise, just so you agree with me. So this is my FA, and if I AND it with F0, I get F0. Now that I have masked away the bits that I want to keep and I have zeroed out the bits that I want to modify, I can now OR it with the value that I want and get the value that I need while this marker dies. And that guy actually saw it. Good. Okay, questions on this, because it might have been years since you've done this, maybe especially for our seniors. Here's the fundamental part. You're taking a value and you're going to create a mask. You put a 1 in the mask for every bit you want to keep. You put a 0 in the mask for every bit that you want to modify. All right? Then you want to OR in the new bits that you want to set. Let me try this a different way. I'll leave this here. If I wanted to change this to be CA instead of FA, so let me say here that my goal is now CA, what is going to be my mask? Like, what am I going to AND this value with such that I nuke these, but I keep these bits? Travis? 0F. So I'm going to take CA, and now, of course, I can't remember what C is. It doesn't really matter. Let's see. So if I AND CA with 0F, then I end up with, did I get C right or no? You know what? People give me conniptions about things. Where's Ashley? Ashley's in here. I'm not standing for this. So now you get the, these actually all go away because it's ANDing. So now you get zeros. And what you can do, now if I want to make this C, do I just OR this? It really was F. So let me, CA, it was this. Now we're good. If I wanted to make this a C, if I OR in C over here, I just overwrite these bits. What I'm actually going to OR it with is C, but shifted over 4 bits. So what I want to do is I want to OR it with this value here. So this is my C, but it's shifted left 4 bits. And I get the value, bless you, I get the value that you want. So the general format is going to be your value ANDed with the mask, ORed with the new value. Okay? And I've got plenty of slides on this, but I wanted to sort of do it manually so that you get a general idea. Same thing here on this example. If I've got a 16-bit value, I want to change the lower byte. I want to modify the lower byte to be 34. I set up my mask to be FF00. So that means that I keep AB and I get rid of the lower byte. I now then OR in 34 and I get the value that you want. What you may start to see is that the mask here is always the size of the stuff I'm keeping, and then it's shifted over by 8 bits. So we're going to start to do a lot of bit shifting and ORing so that you can write a single mask and you can write a single value, but you shift it into place. So if you were writing code, all of these Boolean operations use the single or use the basic bitwise Boolean operator. So it's not a comparison or a comparison and, so it's a single slash or a single and that gives you the logic that you need to do this. Now, it gets trickier, as I said, based upon the location that you want to modify. Let's say that you want to modify this B and you want to make it a 2. You can AND everything with F0FF, and that will nuke this one, and then you can shift over that 2 that you want. But the way that I want you to start writing, these operations, because I think it's more efficient, is that you figure out the width of the field that you actually want to modify. You shift it over to the position of the field that you want to modify, and then you invert it. So that is another way to define what your mask is. So the mask in this situation was F0FF. This is an equivalent definition of the mask. This will give you the exact same value. And the way that I write all my masks this way is because it says, I want to modify a field this large that is 8 bits over. And then when you invert it, you actually get the correct mask. So what it allows you to do is to say, I want to modify 4 bits, 8 bits over, and I want to put a 2 in that location 8 bits over. And so the way that this ends up looking, as opposed from last time, is to say the pointer is ANDed with the mask, this mask, and I'm putting 2 in it. So in my mind, this is a little more readable, saying I'm going to destroy an area of 4 bits that is 8 bits over, and I'm going to put a 2 in that area. Darren?
What's the difference between shifting over 8 bits versus just ORing 0x2000?
Nothing.
Is it just more efficient?
No, they exactly compute the same thing.
Okay.
It's less stuff to type.
Right.
And this can be generalized. So in your lab, you'll have a function that will modify certain bits, and the way I implement it as what is the bit position you want to write, and what's the bit value. And then you can generalize this to work on any combination. Otherwise, you're doing this by hand every time for every different register. Okay, I'm going by 3 this time. I'm going by 4. Oh, this one's only 2 bits wide. Like, you're changing it. But you can write a single function that takes a mask and takes a position and takes a new value, and if you follow this convention, you write a single line of code that does all of your modifying. You just pass it different parameters. So functionally there is no difference between what you wanted to do, what you were describing doing here, and what I have written here. There's absolutely nothing different. The compiler will actually render it as this. No, not necessarily. It'll actually do these operations. It'll unfold into a constant. And then it may, since this is a constant and a negation, it may take it and automatically do it for you. But if it's variable, it'll have to calculate it. This can be turned into a function that you can modify any field of any size. This you have to write out every time you want to modify something. So if you don't follow this method, you can just, for this lab, perfectly fine with me for you to write out every single bit transformation by hand. You're going to drive yourself nuts after a while because you really want to write it like this. You want to try to generalize it. At the same time, you may want to make something that is a pound def that is, if you know you're modifying, let's say, the mode of a register and it's 4 bits wide, you can say pound def, pin mode mask, and you know the width of the field. And that's actually what the data structures inside of your libraries do. Right here. So Darren, to your point, the files that you have will have all these shifts and pounds and everything defined, and so that's why you do it that way, because they have everything already labeled. Now, you can write out all of the widths of the field by hand. You can move everything by hand. What you're going to find for your actual implementations on the GPIO is that a lot of the header files have defined the size of the mask and how many bits it needs to shift, and it defines what values need to go in it. So if you look at this line of code here, all this is doing is the exact operation I told you about, a mask and then an OR, but it's doing it with everything predefined. So it is setting the drive mode of some GPIO port. So it's going to the GPIO data structure, it's looking up a certain port, and it's accessing the control register. It is reading that register, then it is ANDing it with the mask that it needs, then it is ORing in the desired mode at the correct position. So what this function does is you don't have to tell it modify bit 3 and 12 and whatnot. You have to say, given a definition of a port and given a definition of a mode, it knows where all these things are located and it sort of does it for you. This is better because it contains your errors in one place. Meaning if you have 20 lines of and this, shift this, and this, shift this, and you're not fundamentally doing the read, modify, write correctly, it's going to be hard to figure out where your error is. This encapsulates it in one function that you can debug and figure out. At the same time, you may want nice little helper functions to help you out. I will give you these to start with. So there are some helper functions that are in Lab 1 that help set modes and help set outputs, and you may want to implement functions that look like this. So using the shifting and using the modifying, I can give you any address, and I can give you a bit position anywhere. And what it does is it takes that address and it shifts it down to the position that you want, and then it ANDs it with 1. So let's say that you want the 8th bit in some register. It's going to take that register value, shift it down 8, so that bit is in the 0th or the final position. Then it ANDs it with 1 and returns that value. So let's say over here, I had a register that for some reason looked like that. It just had some random value. And I want to know the value of the bit in the 0, 1, 2, 3, 4th position. What this line of code does is it takes this and it shifts it down 4 positions. So the end result is this value. So these numbers come all the way down. Then when I AND it with 0, 1, I actually get the value of that individual bit. So this read and then shift to the position I want and then AND it gives me a single bit. You can also see how you can use this to modify a single bit. So I read the address into a register. Using my convention, I want to nuke a single bit at a certain position. So this is creating my mask. Then I want to OR in whatever value I want that bit to be into the correct position. And I've actually renamed this function in the lab to call this position, POS for position, because calling it bit is kind of bit and value, what's the difference? All right. Who feels really good about these two notions here about shifting and ORing? Who feels less than okay? So everyone's sort of like, meh, I'm okay. Okay, that's fine. It'll make more sense once you start to do it in practice as well. You need to get to this level of understanding so that you're not spending the entire class twiddling your bits and not just modifying single bits the entire time. So this is a good place to be in terms of generalizing functions to do things for you. Bill. Good question. What happens if I'm an idiot and I pass the number 32 in here? So Bill's question is, why does value have to be ANDed with 1? It has to be ANDed with 1 because what if I'm a stupid person and I passed A? This is intended to be a single bit. What happens if I pass in A or D or 37 or 1 million? I don't pass in a thing that is a single bit wide. This ensures that the value I only modify 1 bit. It's a safety precaution. It's a sanity check on the inputs because this is an unsigned int and you can technically only pass in, you can pass in anything there. If you wanted to really commit, maybe you could make that actually a Boolean, but some things don't understand Booleans, and so we're just going to make it, actually in the code, that should be a uint32t. You just make it that, and you OR it in, and you're happy. And you sanity check your input. More helper functions that you may want to find, but what you will see in all of these helper functions is more of the bit masking, more of the bit shifting. If you want to dig into the libraries that implement your functions, be my guest. Okay. Your lab over the next week is going to be very simple. You're going to turn on some lights. You have 2 LEDs on your gecko. You're going to turn them each on individually. Then for the coup de grace, you're going to click a button. It'll turn 1 light on, and you'll press and hold another button. And while that button is being held, you'll turn on that LED. Functionally, it's not that spectacular, but it'll probably be about 20, 30 lines of code for you to get this right. There are overall 3 ways that you can do this. There is a library provided with the Giant Gecko that makes GPIO function calls. You say GPIO mode set, pin out, read in, and you just pass it the name of a port, and it'll automatically do this stuff for you. That's nice, but you really want to understand what's going on under the hood, because one day you're going to have a system that doesn't have nice function calls, or the function calls are broken, or it conflicts with another library, and you need to understand the actual data structures that are underneath. So there is actually a GPIO struct, it's not a class, it's a struct, that lives in the same memory location as the GPIO peripheral. Modifying that struct is the exact same thing as modifying the GPIO port itself. And then finally, the last thing that you can do is you're going to have to do everything by pointer math. You're going to have to do everything by Boolean ands and shifts. I will make you do the entire lab like that for the final task. It's the last time I will make you do everything by purely pointer math. You will still have to do pointers and you'll still have to read registers, but from here, from the rest of the course, we're going to start here and go on. So you'll just be working with the internal data structures. Silicon Labs has provided a very rich and wonderful library. It's called emlib, and it works for all of your peripherals. Some of the stuff is well documented and works well. Some of the stuff like SPI and I2C is really, really wonky to use. The GPIO works pretty well. You've got function calls that set the drive mode, that enable debugging. You have constants. Instead of setting mode to 4 or 3 or 7, they've already defined constants for you. So instead of saying, 4 for push-pull, you'll have a constant that says GPI mode push-pull. They've already got predefined constants that have the correct binary value for you. So if you want to make your pin a push-pull, you will use the GPIO set mode function. Then you will pass it the constant GPI mode push-pull. Behind the scenes, those are all just pound defines that are a special number relative to your system. This, to turn on the light on your processor, this is 2 lines of code for you to turn on a single light. There is an application note that you're going to have to read, application note 12. All the application notes are on the website. The application note tells you how to use the library and how to use the data structures to modify the GPIO. You're going to need to read it to figure out how to turn on one of the LEDs. And one of the LEDs is located at PE2, port E, pin 2. So the really, really easy way to do this is the pin mode set command. So read application mode 2 and use the pin mode set command, and that will do it for you. Now, the real sort of programmer way, and the way that it's probably done, generally done in practice, is that there is a data structure, and this was again to a question we had on Monday. They have defined a data structure that has the exact layout of the GPIO peripheral. And then they have told the compiler, or the linker technically, that that data structure lives at the base address of the GPIO. There's not actually any memory there, but there are the registers for the peripheral. So the impact of this is that when you modify one of these registers, you are in fact modifying the values in the GPIO peripheral. So what they have done is that they have defined the general registers for the 6 ports, the 6 GPIO ports that you have, and then these are all of the other configuration registers. This is a struct and not a class. Why is that distinction important? Why is it important that this is laid out in a struct and not a class? What do you think, Ben?
The class will take or add additional space that's not necessary.
Okay, that's one thing. That is one aspect. A class is a little more heavyweight. You've got constructors, you've got fields, you've got methods. It's a little more than you need. What is the difference? Bill, what do you think? Okay, that could be another reason, but if I make it static, it's always on the heap anyway. A struct is laid out contiguously in memory. It is compact, meaning that if my struct has 4 ints in it, and each int is 32 bits, it takes up 4 words exactly in memory. A class is not guaranteed to be laid out compact or contiguously in memory. So if you have, so like when you make an array and you when you ask for 8 bytes, you get 8 bytes in a row. Same thing with a struct. They have a data structure, a port definition of a data structure that is exactly the same as the actual port. So remember that this PA control register is 32 bits. If you make a variable that is 32 bits wide and you say that that variable lives at the address of that register, they're the exact same link. The structure sits over top of the peripheral. So when you modify the structure, it doesn't actually live there, but you tell the compiler it lives there, and so that way the compiler reads and writes that peripheral because it's memory. And this is why stuff is memory mapped. So your computer thinks you're reading memory, even though you're actually reading an external device. If you tell the program that this data structure lives in memory, it tries to read it, and in trying to read the data structure, it actually reads the registers that you want. So that is the major benefit of having something memory mapped, is that the CPU does not need special instructions to access the peripherals, it just reads them. So, as I said, there were 6 ports, and each port is defined as a 32-bit control register, a 32-bit mode register, a 32-bit mode H register. So that port definition is the exact same size as the actual port in the memory layout. So if I modify those, it modifies the data structure. The important thing here is that you simply tell the code, the program, where the data structure lives. And the way that you do that is that there is a pound define that says, well, my I2C peripheral is actually a pointer to some memory location. It's a pointer of that object's type, and it lives at a certain memory location, which is going to be 4,000, 6,000, or whatever it has to be. So, when you are using this data structure, so when you're using the data structure to modify the GPIO, it's like you're modifying just a regular old data structure. And if you want to access port 2 of the GPIO and its mode register, you say GPIO, dereference the pointer, you want port 2, and then the mode L register. And so that gives you that actual register. So instead of writing a pointer and dumping it down into a variable, you have this right here. At the same way, if you wanted to set the mode of a particular pin on port 2, you could say, well, its mode L register is equal to its value ANDed with the mask, ORed with the value that you want to OR in. Nick, yeah.
What's that first line of code?
Yeah, something's like truncated off of it somehow. It's just there to look pretty. I think we're missing a parenthesis over here to actually read this in. It's from the application notes, so you can look in the application note and see what it says. This line right here goes to the second port, the D-out register, and it sets the 5th bit in the D-out register. Travis.
So why are we not in the max?
Because that's the way I'm doing it. Okay, so.
But wouldn't we need to not the mask and shift it?
This is the mode 5 mask. They've already pre-shifted it for you. They've already said that since it's mode 5, they've already done it 5 over. So some terrible programmer for each one of these had to write down mode 1 mask, mode 2 mask, mode 3 mask. They've already done it. If you want to look into it, you can, through Simplicity Studio, jump in there and actually see what the exact mask is. Let me see if I have it on the next slide. I don't. Yes, you should be. If you define the mask generally as the mode is 3 bits, then or 4 bits, that's your mask, and you have to ship it over. This one has already done it for like the 5th position. So they have got 8 of them for this, and then they've got 8 more for the upper one. You have to do whatever way works. I invert it because when I define the mask as the position I want to modify, and then I invert it to get all the other bits. That's generally how it's done. Is that the mask is the bits you want to modify, and then you invert it to save everyone else. You don't have to do it that way, but that's generally how it's done if you look at the code that's all throughout here. Okay. Mode 1, way 1 is function calls. It's like you're writing Arduino code and you're not really an engineer. 2 is you're doing it with a data structure. And 3 is you're a super engineer and you're doing it via all complete pointer map. Now, that means writing a pointer to every location, reading it in, manually modifying it, and then writing it back. So what I will say is in the lab, your final task of doing the buttons, you have to do that all with pointer map by yourself. What you should do is write functions that are written in pointer map that help you, like read bit, write bit, read mode, set mode, those fun things so that your code is actually readable and it's not full of bit shifts, ors, and ands. Things that may help you. Silicon Labs provides a lot of software. When you're looking at the software, make sure you look at the Giant Gecko software. Also, there's the link to the peripherals library. Make sure you take a look at that when you're doing the GPIO calls. So what your lab, and I have this more written out. This is just your introductory slide. And actually, I think for this one, I say no emlib calls, so you can use the data structure if you wish. Make yourself happy. You need to turn on this LED using the function calls. Do it. You need to turn on this LED using the data structures. Do it. You need to turn on this LED using pure just pointer map. So the final task then is to do the push buttons, where one button, if it's pressed, then PE2 illuminates, and if PE1 is toggles PE3. Now, LED 0 is connected to port E2. LED 1 is connected to port E3. You have two push buttons on your board. They are unfortunately called PB0 and PB1. They are not actually connected to port B0 and port B1. So it can be really confusing when you try to figure out what ports they actually live on. If you look up the user manual for the Gecko, it will tell you. Don't look in the reference manual. The reference manual is way too sort of detailed, and it's hard to find. Look in the user manual or the data sheet. If you're trying to figure out the layout of the pins or something sort of consumer level like that, start at the user manual or the Get Started guide, something kind of higher level. If you want to know very, very low detail stuff, go to the reference manual. So I'll go ahead and I'll tell you that LED 0 is on port E2 and LED 1 is on port E3. I'll let you figure out how the push buttons are connected. Let me show you what the assignment looks like. And I have taken the videos from last week and also this one, and I've put them on my now YouTube channel. So, I know, yeah. Yeah, you have a work Gmail account, which means you have a work YouTube account. So, I will put them up there. Let me know if they're actually helpful. My concern with this guy is that he's never actually going to pick up the screen, but it might be able to pick up the board. But at least you get my audio. But if all you've got is audio, like I can just wear a microphone, and we don't have to record me. This is what your... No, stop. Why do you treat me like that? Oh, I have no idea. I'm just gonna. I don't even think it has like a channel name. Like it's just because I have a work account. Because all of our emails are Gmail, right? Okay, so that means I have a YouTube account with my work address, and that automatically uploads to it. But I have no idea like what the channel name is. Like I'm still figuring that out. Yeah. I hope that returns nothing, and I'm pretty sure it will. Wait, are you saying it actually comes up?
Yeah, I think that would.
Oh. Well, that's just my clock, though.
The GPIO part
is next. Okay. So I think if you click on me and then you click on my videos, like the GPIO should be there along with some greenhouse stuff. Okay. Stuff you're going to need. You're going to need to have this lecture. You're going to need to read application note 12. You're going to need the Gecko board user manual. And you're going to need the reference manual. The user manual is going to tell you what pins are connected where, so you can figure out where the push buttons are. The reference manual is going to give you all the evil little details that you need. You're going to make lights turn on and off. Your grade will be on functionality and will be on the clarity of your code. So add some comments, but this is a performance-based industry. If your light does not turn on, then you don't get credit for it. So looking at the weighting, about 50 to 60% of the lab are these first three tasks because they should be easy. This is extremely easy. So do these three right here. That's about 60%. The remainder of the lab is sort of doing with the push buttons and the LEDs. So what you're going to do is while push button 0 is held down, LED 0 should be turned on. Think about how you would write that out as an algorithm. So as long as this button is turned on, this light is turned on. The second one is push button 1. As long as push button 1 is, every time you hit push button 1, it should toggle the LED. So if you hit the button once, turns it on. Hit the button again, turn it off. Toggle, on, off, on, off, on, off. That one's harder because you're going to have to keep track of the state of the button and the state of the LED at the same time. Karen, yeah.
Could you just use interrupts.
You could if you wanted it to go on to lab 2 and use interrupts.
But there's hope.
I mean, you're gonna trust me, you're gonna have timers, and timers are gonna interrupt and cause lights to blink. You don't want that headache yet.
Okay, good. I'll just pretend I didn't say it.
That's fine. Think about it this way. The thing with buttons, you hope the buttons are debounced. And they may or may not be. By debounced, what I mean is that when you press a button, it is not an ideal edge. So if the button is naturally high and you press it, it is not a natural straight edge. What actually happens is that it takes a while to settle down. These buttons, I think, are actually debounced and you don't need to worry about it. So I think you can treat them as a normal edge. But in a system that you're creating, if you're doing it sort of on your own, you're going to need to debounce buttons. And you're going to have to wait for them to oscillate out. Where's the mouse? All right. Let me show you the code that I've got. All right, so I have created a GitHub page where I'm going to put the code for this class. So my GitHub name is York CPE. There is a repository called ECE 370 2018. So what I have put up here and what I will continue to put up here is, so this was the code, this was the project for your assignment 1. And so what we're going to do, once I nail down all the bugs with this, is that we're going to put Git on all your machines. And instead of me uploading files, I will just push to Git, and then you'll just import them to your computer, and it'll just make life easier, especially if I have to push changes. What you also have up here is some example projects. So this is the read memory project that we kind of talked about in class. So here's some little example code that goes over like how to read memory. So if you didn't rip it out of the slides, you've got the code here that's doing sort of the read memory. Some of these are uploaded as actual projects. So if you see a structure that looks like this, where it says debug emlib source, this is an actual project and can be imported directly into Simplicity Studio. I'm having bugs where, depending on when you install the software, you get a different version of the SDK, and then you get a wonderful error message about incompatibilities and compiler toolchains. And so once I make that clean, I will start putting your projects up here, and you will just import them. But until then, what we're going to do is just, if you come down here to Lab 1, this is your Lab 1. No. This is your Lab 1 code. No, stop. So what I want you to do is just make a default project. Just make a default project. Open up the Blink example from Simplicity Studio and then copy and paste this main file in. Or Blink's.c file, doesn't really matter. But what you've got is I've left a bunch of comments. So some places where you might want to define some ports, where you might want to do some pound defines for some port addresses. Here are some helper functions that you may choose to implement. So there's a helper function that does a read bit. I've just given you that function in the lecture. You should copy it in. I have given you a function that writes a single bit. Man, that might be useful if I want to read the value of a pin, and man, that might be useful if I want to set the mode of an output pin on a GPIO, if I want to make it high or low. I have put nice sort of Java doc style comments. I advise you just sort of follow this paradigm where I have a little description. I describe all the parameters, and if there is a return value, I tell you what the return value is, what it means. Down here you have a main function. Ben, can you read this in the back? Is that big enough? Okay. Down here you have a main function. I turn on the clocks for the high frequency peripherals and the GPIO. We will talk about this in more detail, but for right now, understand that all I do is just turn on the peripheral for you. You don't need to turn it on. Right here, under task 1, I want you to turn on the light using the library calls. So write 2 lines of code here that will turn on an LED. Once you've done it, comment it out, move to the next thing. So you're going to have code in here that you want to keep, but you don't want to delete. So please don't write your code and say, oh, great, it works, and then delete it out. Because I'm going to come back and grade it and go, oh, well, Jason didn't have any code under task 1, so I guess he didn't do it. Like, just leave your code in there. Because I can quickly see whether it works, and I can also quickly uncomment and see if it works. So what I'm going to do with all your projects is I'm just going to uncomment certain bits and see how they operate. I'm not as fancy as Dr. Muscola, who would have an entire test bench to do this. I'm just a little too lazy for that. So task 2 is to use the GPIO data structure. When you dereference it, you get a P, and the P is the particular port that you want. It is an array. If you wanted to access port A, it would be P0. If you wanted to access port B, it would be 1. So make sure you read the application note to help you understand how to access that data structure. Part 3, pure pointer math. So use pure pointer math. You can use functions if you like, but only if they're implemented with pointer calls and not with emlib calls. Your last bit of code. I left these 2 blocks here intentionally. You're going to have some sort of setup for the last task, and then you're going to have some sort of ongoing functionality for your buttons. Do not remove the while loop. If you remove the while loop, then main will exit, and the code will begin executing where it'll return from main, and you'll begin executing it like memory location 8. You'll be executing in the middle of nowhere. You will probably actually just restart. So you'll be way more functional than these lab machines, but